Hello Year 12 and welcome back to the lessons on quantum physics. This lesson will continue on from where we left it in the last lesson, which was on photons. So photons. Now in 1901, Max Planck, the very famous theoretical physicist, he looked at something called blackbody radiation, which is a topic that you would have covered at GCSE, but we'll come back to it and explain what blackbody radiation is in more detail as a refresher. Now, what Max Planck theorized was that radiation is emitted in discrete packets of energy known as quanta. He then looked at the energy of each quantum of energy he might have had and found a link between the energy and the frequency, and he found that the energy was directly proportional to the frequency. And in order to turn this into an equation, there must be a constant. That constant is called the Planck's constant. Now, in 1905, Einstein said that energy isn't just emitted in discrete packets of energy, but it actually continues. And this concentrated packet of energy has particle-like properties, given a symbol a bit like this, to show that it's a discrete little packet of energy, and this is what is called a photon. Now, in order to get a better understanding of what Max Planck was doing, it's important that we understand a little bit about blackbody radiation. Okay, so here we have some filaments of a light bulb. Okay, as you turn the electricity on, that filament starts to glow. The more current that flows through it, the brighter the bulb. If something is hot, it may glow bright red, as you can see the picture on the very far left. But if it gets hotter, it may change color right up to a very white hot filament, which is on the far right there. There is a relationship between the color of the filament and the increasing temperature. It's not actually one color that's being emitted, but a whole host of colors being emitted. So here is a representation of part of the electromagnetic spectrum in terms of the light. And down the bottom we have infrared, and at the top we have or would have ultraviolet. If something is quite warm, as you can see on by the left arrow, it will release heat energy, that is infrared energy, but will also start to emit some light as well, initially in the wavelengths that are the longest. The hotter the object gets, it will start to emit light in the orange and yellow part of the spectrum, as well as the red. Even hotter still, and we get infrared radiation and red, orange, yellow, and green light emitted as well. When it's even hotter, we get the smaller frequencies as well as blue and violet. As we're seeing the whole spectrum, it appears white, plus we're also getting the infrared radiation as well when it's really hot. There is clearly a relationship between how much wavelengths are being emitted and the temperature of the substance. Now, some important points to be aware of as well. As substances are heated, they start to glow. The hotter they are, the more they glow. The pattern is dependent on temperature and not the substance used. These curves that are shown on this slide are called the blackbody curves. On the y-axis, we have the intensity, which is the power per unit area, or how much energy is transferred to a given area in a certain amount of time. And on the x-axis, we have the wavelength. What the graph represents for a particular temperature is the range of wavelengths that are emitted. If I have a temperature of, let's say, 5,880 Kelvin, as shown in the top curve, that is the temperature of the sun. What it shows you is that we're getting a lot of infrared radiation. We're getting a lot of light energy with a full range of the visible spectrum, and as a result we would see it as white light. There is a peak which is in the green for that first graph at the top. If I decrease the temperature to the temperature of a light bulb or a filament bulb, which is about 2910 kelvins, there is a lot of infrared radiation emitted, but not much light. And this infrared radiation emitted is shown by the black region underneath the red line of the graph. Okay. So there's a lot of infrared radiation emitted, but not much light. There's not much in the smaller wavelengths, but a bit more in the red and the orange, as we can see from that diagram. Now, in the old style light bulbs, 90% of the energy is converted into heat energy, and here it is shown as infrared radiation in the infrared section under the graph. Just a little bit is converted into light energy. As you can see, just a little bit of that visible light spectrum falls into underneath this curve. Okay. As the temperature goes up, the peak moves towards the left, and the wavelength gets smaller. Okay. Now, hotter objects give out more of every wavelength of radiation than a cooler object does. Okay, so that's worth remembering. Now, if I want to take accurate measurements, then I need a substance that absorbs all the electromagnetic radiation before emitting it, and no radiation should be reflected or transmitted by that object. The light that's given off an object is purely what's converted from what it already absorbs. In other words, if I have a light blue object like the circle shown on the left-hand side, it's light blue not because it's hot, but because it's reflecting light. So really, if I were to heat up a blue object, it's not helpful because I'm getting some radiation due to reflection of blue light. If it's a bit darker, like the circle shown there in the middle of the diagram, there's less blue light, but it's still not ideal. What I need is a perfect black substance. It is not reflecting any light. It's simply absorbing everything. Then it re-emits it as heat energy. Here you feel, for example, hot if you're wearing a black t-shirt for that reason. No substances are perfect black bodies because as long as you can see them due to just a little light reflected off of them, then they're not perfect black bodies, like a t-shirt. Okay, we can still see the black t-shirt. But some good examples of very good black bodies would be stars, our sun. It's not reflecting any light, it's re-emitting light from all the fusion energy being converted inside of it. An oven is another example, absorbing all the energy, and then it starts to glow only when things start to get hot. So a black body is simply something that re-emits all its energy that it absorbs. It's a perfect emitter and perfect absorber of radiation. So here in this diagram, we have basically a picture of the black body curve again. So ignore the white line just for the moment. The black body curve is focusing on the red curve there, which was the experimental data taken by measurements. Okay. Now, it was a bit of an enigma to scientists in the latter half of the 19th century because scientists wanted to describe the behavior of the intensity and wavelength that this particular graph represents through some sort of mathematical formula using their classical understanding of physics, thinking of electromagnetic radiation in terms of waves. Now they got a result that described the first part of the graph. So if you can see the white line to begin with seems to be following that the experimental data to begin with, but their maths predicted that the curve would continue upwards as it does in the white line. Okay, so that was through classical wave theory and mathematical modeling. So as an object gets hotter, you get more and more smaller wavelengths of much greater increasing intensity, i.e. you could get substances that release a lot of ultraviolet radiation and X-rays. But the problem was that it doesn't represent what we actually measure. Okay, so for the classical idea that light and electromagnetic radiation are waves, then the behavior should go up like the white line. But the actual experimental data follows the red curve. Okay, so the question then arises: is the physics right, or is the experimental evidence correct? Now, unfortunately, the physics broke down at the ultraviolet range. Okay, so they call this the ultraviolet catastrophe, where the classical wave theory no longer followed the experimental data. Okay, so it was basically demonstrated that the best understood classical laws of physics were incapable of describing the radiation properties of hot objects. The wave nature of light, in other words, cannot explain how an object can glow when its temperature increases. Now, in 1900, Max Planck was perplexed, just as everyone else was really, by the inability of the physics understanding to explain the experimental evidence of the black body radiation curve. What he did say was that, and what he did know, was that atoms are releasing electromagnetic radiation. The atoms themselves can also receive radiation and then convert that into other forms of radiation. He thought that maybe the energy is quantized, or that energy comes in these discrete little packets. He suggested that the energy value was based on the frequency multiplied by a number that he determined. And this number was basically what we now know as Planck's constant, 6.63 times 10 to the power minus 34 joules second. Okay. He said that an atom can absorb either 1 bit of energy or 2 bits of energy, but it can never absorb 1.5 bits of energy. For example, let's say we could use the analogy of someone going up the stairs. Now, as you go up the stairs, you are increasing your potential energy. You either can go up 1 step, perhaps 2 steps, but there's no way that you can climb 1.5 steps or 2.5 steps. So the energy is quantized. Now, if we think of a slope, which is shown on the diagram on the right-hand side, the bottom right-hand corner, a slope, on the other hand, is not quantized. Okay. Now, imagine that slope, though, at a microscopic level. If you did look at that slope on a microscopic level, it would actually look like a staircase. It would not be continuous like the slope is in the diagram at the moment. So on a microscopic level, that slope is still quantized, except that the steps are really, really, really tiny. Planck was saying basically that energy is quantized at the really, really small scale. Normally, we treat energy in terms of something that's continuous, but at a very smaller scale, it is quantized. Planck reconfigured classical wave mathematical formula to allow energy to be quantized using his constant. The data formed a lovely curve, and for a particular wavelength that he determined with, he got the curve and it matched the experimental data curve as shown in this diagram here. It was only a mathematical explanation to fit a formula to the data, so it's worth noting that something very important is that you couldn't really marry the concept of energy being quantized with physics theory on energy at the time. That would be resolved a couple of years later by Einstein and his work on the photoelectric effect, which we will look at in the next lesson. Here is a picture of the electromagnetic spectrum. So we have radio waves at one end of the spectrum through to gamma rays at the other end. So the idea that Einstein really came up with, along with the foundation and groundwork laid by Max Planck, was that energy exists in these discrete packets of quanta with low energy photons at one end moving through the higher and higher energies, the visible light going from red to violet, then the violet, which is more energetic, then the X-ray photons, and finally the gamma ray photons are the most energetic of them all because they have the highest frequency waves. It's important to remember that photons are massless, so they travel at the speed of light. C. Anything that has no mass only travels at the speed of light. Anything which does have mass can never get to the speed of light. When you see the stars at night, it's basically a photon must have been emitted by that star maybe millions of years ago, and the first thing it'll hit after traveling through space for maybe millions and millions of years is, amazingly, the back of your eye. That packet or bundle of energy has caused that signal to go to your brain to let you see that star. Okay. So the important equation that we need to remember is that E is equal to HF, which is also because of the fact that we can combine the wave equation with the energy of a photon equation. It's the energy of a photon is also equal to hc over lambda, h being Planck's constant, c being the speed of light in a vacuum, and we divide it by the wavelength. So what is the energy of one gamma ray photon? Well, gamma rays typically have frequencies greater than 10 to the power 20 hertz. Now, the energy of a gamma photon is therefore greater than 6.63 times 10 to the power minus 34, Planck's constant, multiplied by the frequency, which is 10 to the power 20, which means that they will have an energy that is greater than approximately 10 to the power minus 13 joules. This is a very, very small amount of energy on a human scale, so we don't notice the effects of individual gamma photons. However, some astronauts in space have reported seeing flashes of light as individual cosmic rays, which are high energy gamma photons that have passed through their eyeballs. Now, as we've already established, the energy of a photon is extremely small and far less than a joule. So the joule is not a very convenient unit for measuring photon energies. There is another unit of energy we use called the electron volt when considering amounts of energy much smaller than a joule. Now, here we have a diagram of a cell, which is a cell of 1 volt. And it's connected to 2 plates, a positive plate and a negative plate, and inside we're imagining that we have 1 electron. So when an electron like this travels through a potential difference, as we know, energy is transferred. If an electron, which has a charge, as we know, of size 1.6 times 10 to the power minus 19 coulombs, travels through or is accelerated through a potential difference of 1 volt, its energy change W is given by capital Q multiplied by capital V. In other words, the charge on an electron, which is 1.6 times 10 to the power minus 19 coulombs, times the 1 volt, which gives us an energy of 1.6 times 10 to the power minus 19 joules. Okay? So work done is equal to charge multiplied by potential difference. So the official definition of an electron volt, also written as 1e capital V, is the energy transferred when one electron travels through a potential difference of 1 volt. Okay, and 1 electron volt is equal to 1.6 times 10 to the power minus 19 joules. Okay, so when an electron moves through 1 volt, 1 electron volt of energy is transferred. When an electron moves through 2 volts, 2 electron volts of energy is transferred. When 5 electrons moves through 10 volts, a total of 5 times 10 or 50 electron volts of energy is transferred. Okay, now 1 electron volt is really a small amount of energy. We have to think about how small the particles are. And the mass of an electron is about 10 to the power minus 31. Okay, so it's really, really small. Now, it's quite useful to know that if you want to convert from an electron volt to joules, you just need to multiply by 1.6 times 10 to the power of minus 19. On the other hand, if you want to convert from joules to electron volts, you simply divide by 1.60 times 10 to the power minus 19. An example here, so if you have 5 joules, if you want to convert those 5 joules into an electron volts, then you need to take 5 of the joules and divide it by 1.6 times 10 to the power minus 19, and that gives you 3.125 times 10 to the power 19 electron volts, which is what 5 joules is worth. Okay. And here is a little example that you may want to use to help you to remember. If you're going from electron volts to joules, you multiply by 1.6 times 10 to the power minus 19. If you're going from joules and converting to electron volts, you divide by 1.6 times 10 to the power minus 19. So what I would like you to do now is take some time to answer questions number 1 to number 3. Okay, so you can pause the video here and have a go at those questions, see how you get on. So how did you get on? I hope you got on well. Here are the answers to question number 1 to 3. So compare them to what you've done, have a look, and make sure that you understand how to answer those questions. So pause the video and have a look at this. When a charged particle is accelerated through a potential difference V, its kinetic energy increases. For an electron with charge E accelerated from rest, we can write the following equation. Ke, kinetic energy, is equal to half mv squared, as we know, which is also equal to EV. Okay, now we can rearrange this equation to give the electron speed V. Okay, so the first thing that we would do, if you look at step 2, in the little white box there, if you look at the second line, we are going to first of all multiply both sides of the equation by 2. In the third and final step there, in the white box, what we do there is divide both sides of the equation by m. Okay, so we've now got v squared isolated. And then if we take the square root for both sides, we can work out the speed of the electron. Okay, now this equation applies to electrons, but it also applies to protons with the charge of plus E and ions as well. Now what I would like you to do is have a go at question number 4. So pause the video and see if you can answer this question. How did you get on? This is the answer to question number 4. So compare what you've done in terms of the working out, the steps and the answers as well, and see how you got on. Okay, so you can pause the video to compare that. We now come to the final part of our lesson, which is an important practical where we can determine an estimate of Planck's constant H by a simple experiment using light-emitting diodes or LEDs of different colors. If we look at the IV characteristic for an LED, as shown on the graph, what we find is that if there's a negative potential difference, the current it lets through is 0, and there's a certain point at which suddenly it starts to behave like a conductor. It conducts in one direction only, the forward direction. It requires a minimum voltage called the threshold voltage, marked in green on the graph, to be applied in this direction before it allows a current. LEDs of different colors require different threshold voltages before they conduct and emit light. For example, red LED emits photons that are of a lower energy and requires a lower threshold voltage to make it conduct. On the other hand, a blue LED emits higher energy photons and requires a higher threshold voltage to make it conduct. How are photons produced? Well, the electrical energy lost by a single electron passing through the diode reappears as the energy of a single photon. Okay, so therefore we have the energy lost by an electron is equal to the energy of the photon. In other words, the energy lost by the electron is EV, which is equal to the energy of a photon, which is hc over lambda, where V is the threshold voltage for the LED. Now, usually when you're doing this experiment, it's possible that the wavelengths of each of the LEDs for the different colors is given on the packet, or you can always look it up on the internet. But also you can actually do another practical where you can find the wavelength of those particular LEDs using the diffraction grating method that I have put up on this slide. So pause the video if you want to recollect how you go about doing that. Okay, and instructions are there. The diagram on the right hand side is the circuit diagram for the setup when using one LED, and you have a voltmeter connected there. You obviously have a safety resistor which is connected next to the LED itself. You have an ammeter as well, and I'll explain why we might need that. And then you have the sort of potential divider bit of the circuit there as well, and then obviously the power supply or the cell. Now the values of the E and C, which are the charge on the electron and speed of light respectively, they are already known to us. So we just need to measure the voltage across the LED when it begins to conduct, and that's its threshold voltage. It is found using the circuit diagram shown, or the picture set up as well. You adjust the potential difference until each of the LEDs just lights up. So as soon as they light up, you take a note of the voltage, and that gives you the threshold voltage. Then you find the wavelength, as I mentioned earlier, of the individual LED by measurements using a diffraction grating, or from the wavelength quoted by the manufacturer of the LED on the packaging. Okay, you can use an ammeter to help you to see when current is shown to be flowing, and that gives you a more accurate reading of the threshold voltage. Okay, because sometimes it's very hard to sense that the light, when the light just comes on. Okay, so we find a range of threshold voltages for different LEDs of different wavelengths, and then we record these in a table of threshold voltage and wavelength there as well. But the most important thing we need to record is 1 over the wavelength. Okay, and then we plot a graph of the threshold voltage against 1 over the wavelength, and we should end up with a straight line through the origin. Okay, this is a straight equation of a straight line is y is equal to mx plus c. Okay, c being the y-intercept, but there's no y-intercept in this case, so we just have an equation y is equal to mx, which is equivalent to potential difference or threshold voltage is equal to hc over lambda multiplied by E. Okay, so the gradient, we need to find the gradient of this line, which is equal to threshold voltage divided by 1 over the wavelength, which is simply equal to threshold voltage multiplied by wavelength. Okay, now we already know that EV is equal to hc over lambda. If we rearrange that equation further, we can get V lambda is equal to hc over E. Now we already know that V lambda is also equal to the gradient m, so we can replace V lambda by m, and then we get m is equal to hc over E, and then rearranging that equation to make h Planck's constant, which is what we want to find, as the subject of that equation, we are left with h is equal to m, the gradient, multiplied by the charge of an electron E, divided by the speed of light c. Okay. The final thing I would like you to do then is to have a go at question number 5, which is related to the practical that we just looked at. Okay, so have a go at that, pause the video and see how you get on. And this is the answer to question number 5. And that is the end of today's lesson. Do take a look at the answers and compare them to your own. There's a bit of the working out there as well. And look forward to seeing you in the next lesson. Hope you enjoyed this.